Hello, grade 11s. This is Physical Science. My name is Gillian. Today, we're going to tackle some questions around intermolecular forces. We called them, or I called them, the friendship forces. So how the molecules interact with one another to give us a phase or the behavior of a substance. So let's look at the screen. There are 6, and they range from the weakest to strongest. So we have the first 3, induced dipole, which is also called a London force, dipole, induced dipole, and then dipole-dipole. Okay, so those 3 are, as a body, called the van der Waals forces. They are the weakest intermolecular forces. Now, sometimes in a question, you will be asked what kind of forces are between the molecules. You can't just say van der Waals forces. You really need to be a bit more specific about that, and you need to then label it. So you can say van der Waals forces, but you then need to say it's either a London force, or it's dipole-dipole, or it's a dipole-induced dipole. So you need to be quite specific about the words that you use. Then we have this intermediate, these 2 kinds of intermolecular forces of intermediate strength, and they involved ions. And so if you remember back, they will be involved with an ionic substance which is dissociated into its component ions. Those ions are then interact with a polar molecule, not a molar molecule, a polar molecule. And if there isn't a polar molecule, they can induce a pole in a non-polar molecule. And the example we had for this was hexane. Another one is sugar, right, or oil. So these are these big organic molecules that really have no polarity. They're non-polar, and as an ion comes past, they will induce a dipole in those non-polar molecules. Our last one is the hydrogen bonding. Hydrogen bonding is very specific. It is very strong. It is between these molecules. So when nitrogen is bonded to hydrogen, so we get ammonia. When oxygen is bonded with hydrogen, and we get water. And when fluorine is bonded with hydrogen, and we get hydrogen fluoride. Only those 3. And the reason why is because nitrogen, oxygen, fluorine are the most electronegative substances in the periodic table. They are the most electronegative known elements that we know about. They are pretty small. They're small molecules, they're small atoms, and they bond with hydrogen covalently, and hydrogen is also minuscule. It's very tiny, and what is left behind as these electronegative atoms pull the bonded electron pair, the hydrogen is left naked, just a proton is stuck out there. So these can maneuver themselves to be very close together, so we get a strong intermolecular force. Right, how we are going to see this is in the behavior of substances. And there are 4 areas that you need to look at. The one is melting point, the second one boiling point, vapor pressure, and solubility. Okay, now what we do know about the behavior of these particles, of these molecules, these substances, is that as their molecular mass gets bigger, as it increases, so the strength of the intermolecular forces between them, their friendship ties, gets stronger as well. And in order to overcome those intermolecular forces, a greater amount of energy is needed to be put into the system to overcome those. And so they will have a higher melting point and a higher boiling point. So that is a really important piece of theory to remember and to practice. So let's have a look at how we could be asked about this theory, and it is quite theoretical. There's not a lot of calculation in this section, so we do need to know First of all, our ionic bonding and covalent bonding, that is the intramolecular forces, or there's another name that's interatomic forces. That's the bonding. We need to know about that. And then we need to know our intermolecular forces and their strengths, what they're called. So the first question says, the boiling points of compounds A to E are given in the table below. And if we check these out, we can see that A is CH4. And as we go down the list, can you see that the number of carbons starts to increase? So the first one, carbon 1, then there are 2 carbons, then there are 5, then there are 6, then there are 20. So that's telling you that these compounds are getting bigger and bigger and bigger, okay? Or these molecules are getting bigger. And let's have a look at the boiling point. So A is the smallest of these compounds, so that's the smallest, and look at its boiling point. Its boiling point is minus 164 degrees Celsius. Have a look at E, which is the biggest, and its boiling point is 343 degrees Celsius. So that's telling you something. That's telling you that as the compound or the molecule gets bigger, the intermolecular force is going to increase in strength. You need more energy to overcome those intermolecular forces, and therefore the boiling point is going to be higher. The first question that they ask you is, define the term boiling point. Okay, so this is a definition. And boiling point is about the temperature. Okay, boiling point, temperature. Boiling point, temperature. I'll say it again. Boiling point is temperature. So it is the temperature at which the vapor pressure is, well, it's going to be of a liquid, right? Because this is a boiling point. So we're going from a liquid, we're going from the melted state into the gaseous state, so liquid into gas. So it's going to be the temperature at which vapor pressure of a liquid equals the external atmospheric pressure. So you can see when something is boiling, you can see, if it's water, you can see the gas coming off. We call it steam, but it's the water vapor, right? So you can see that. And you know that if you put a lid on a pot of boiling water, it will boil faster. Why? Because the vapor has a pressure, and when you put the lid on, it's a closed system, and so the pressure on the outside and the pressure from the vapor is going to equal the pressure on the outside faster. So when you climb up a mountain and you're trying to boil water for tea or coffee, it's going to be at a less temperature. It's not going to be as hot, and that is because the atmospheric pressure is less higher up a mountain than it is at sea level. Okay, the second question is calculate the molar mass of compound D. So let's just check out what is compound D. Compound D is here. It is C6H14. So let's write that down. So compound D is C6H14. We want to find the molar mass of C6H14. We need a periodic table to do this. So let's have a look at our periodic table. So we're looking for carbon. Our relative atomic mass is there. Can you see it? It will be at the bottom of each block. And so carbon is there, and its atomic mass is 12. Hydrogen is 1. So we are going to use those values in our calculation. We've got 6 carbons, and the atomic mass for a carbon is 12. We have got 14 hydrogen and the atomic mass of hydrogen is 1. Once we have worked all that out and calculated it, we get an answer of 86 grams per mole. So grams per mole is the unit for molecular mass. Another name for that, sometimes they ask molecular mass, molar mass is another word. So they all mean the same thing, they're just referring to a different type of compound. Okay. Now, in C it says, in what phase is compound B at 25 degrees Celsius? So let's have a look at B. Well, its boiling point is negative 89 degrees Celsius. So what do you think it's going to be? If its boiling point is moving from a liquid to a gas, it has to be in the gas phase, and it has to be in the gas phase at 25 degrees because its boiling point is so very low. So it is going to be in the gas phase. D, name the type of intermolecular force present in compound A. Now, a clue to this is its boiling point. It is extremely low. So that needs to tell you that these are weak intermolecular forces. Weak intermolecular forces. If its boiling point is so unbelievably low. If we write the structure of this molecule out, we see it looks like that. And it is quite symmetrical. It's a symmetrical molecule, and so it means that it's nonpolar. So this thing is nonpolar. That would be another clue to tell you how very weak these intermolecular forces are going to be. So what is our answer going to be? Well, we know that it is going to be a van der Waals. Okay, so van der Waals force, but we want to be more specific about it, and so we're going to say that this is going to be the weakest because that is a non-polar molecule, and so we're going to say this is a London force. We could also say that it is a induced dipole. Okay, it's not a dipole molecule, it is a non-polar molecule. So that would be an induced dipole, and that's where the electrons, because it's non-polar, will at some instant be collected over a molecule in one place more than in another. And so it is instantaneous and it passes. Right, grade 11s, we are going to take a break now. When we come back, we're going to tackle another question.